Hello everyone, and thanks for joining this session where I'm going to talk about our project called Mria, a purpose-built extension to Mnesia database that adds eventual consistency to the cluster. This talk is not going to reveal any novel research in the field of distributed systems. Instead, I will try to present some of our engineering practices that helped us to develop this technically challenging project in a very time-constrained environment. First of all, let's address the question, is it a good idea to use Mnesia at all, given all the modern alternatives? If you search the internet on this matter, you will find a lot of posts discouraging use of Mnesia. They say it's very tricky to troubleshoot, it has problems with storage backends and whatnot. And these are valid points. In most common scenarios where you need a database, for example, if you're building a web application backend, choosing something else is usually going to be a safer option. But despite this common advice, we at EMQX use Mnesia a lot because it combines certain features in a very unique way, which makes it very helpful for our use case. Mnesia is quite unusual in the sense that it is both embedded and distributed. Embedded databases run alongside with the business logic using them. And they live in the same address space. But on top of that, it is also a distributed database, so it helps us with data replication. One reason to use an embedded database is simplicity. But we are mostly after throughput and latency. RAM copies and disk copies tables in Mnesia are backed by adds. So dirty read queries on these tables become adds operations. And they're about as fast as things can be in Erlang. Because of that, we can read data from Mnesia tables in hot loops, which simplifies business logic a lot. And sometimes, atomic and isolated transactions come in handy too. Before I go any further, let me briefly explain what is EMQX and why we are after these features. EMQX is an MQTT message broker, and MQTT is a PubSub protocol, similar to RabbitMQ, Kafka, and whatnot. As usual with PubSub protocols, we have clients that can publish messages to topic or subscribe to them. There are some unique features to MQTT protocol as well. First, topics are organized in a tree that somewhat resembles a file system with directories. Second, clients can subscribe not just to single topics, but to groups of topics all at once using wildcards. And finally, topics are dynamically created as opposed to Kafka, for example, where the system administrator usually should create topics in advance. This is a very flexible system. It does not require any configuration to enroll new clients. It's very easy to set up authorization rules for the clients based solely on the topic name. And because of these properties, MQTT is widely used in the Internet of Things. So while MQTT is very simple for the users, it means the complexity is pushed into a message broker. One of the biggest challenges when it comes to throughput of MQTT broker is maintaining topic metadata. And EMQX uses Mnesia for this. Routing table and topic tree tables are the most frequently accessed and updated tables in our system. Let's briefly go through the algorithm that we use for message routing. Imagine you have two EMQX nodes. Now suppose we have a client that connects to node 1 and subscribes to a topic. EMQX then inserts a special record into the routing table, and Mnesia replicates it for us. So our nodes know that there are some clients that subscribe to this topic on node 1. Now we got another client. It connects to a different node and publishes message to a topic. EMQX then does a very optimized adds query, added with indexes and whatnot, and finds nodes where this message should be routed to. The destination node then dispatches this message to the local clients that need it, and that's it. This is a very simplified description of the algorithm, but it illustrates how we use Mnesia. And as you can see, it's really crucial to have extremely low latency and high throughput for dirty reads, because they happen for every incoming messages. Now let's talk about problems. We are mostly satisfied with read throughput and latency of Mnesia, but when it comes to writes, especially in large clusters, things start to break down. While we read from the routing tables orders of magnitude more often when we write to them, our database should be able to handle decent throughput for writes as well, because we must handle storms of connecting clients. Suppose there was an odd restart or a network disturbance and millions of clients rush to reconnect and resubscribe to the topics. We should be able to handle this in near real time. Over years of experience, we found that Mnesia write throughput drops dramatically as you scale up the cluster. In the next slides, I will quickly walk through Mnesia replication protocol, and it will explain why it happens. Additionally, our customers sometimes want the ability to scale the cluster up and down. And if you're familiar with Mnesia internals, you already see a can of worm opening here. Now let's break down what happens when you call Mnesia transaction. Mnesia uses leaderless peer-to-peer replication. Data integrity is ensured by a variation of two-phase commit protocol. One interesting detail about implementation is that it is very asymmetric. When a process starts a transaction, most of Mnesia logic runs in the very same process, including running transaction fun and two-phase commit flow. But on the remote nodes, the steps are handled in a dedicated gen server called Mnesia TM. It makes transactions highly parallel, it's a plus, but on the other hand, it makes performance of Mnesia dependent on the surrounding business code in rather unexpected ways. Let's dig deeper. The transaction flow starts from making a call to Mnesia TM process to get a new transaction ID. It also creates an unnamed @bag table, which is used as a shadow storage for the transaction. All side effects of this transaction are written to the shadow store, where they're invisible to other processes. One transaction process runs the transaction fun, where all the reads and writes happens. During this time, it communicates with Mnesia locker process at all. We won't go into details. But once the transaction fun successfully completes, we move on to commit preparation phase. In this phase, Mnesia looks up schema to find all remote replicas of the tables which should be updated. It decides which commit protocol to use, one of 4, and proceeds to the first stage of commit. In this stage, commit records are sent to Mnesia TM process on all participant nodes. Participant nodes then vote whether they decide to commit the transaction or not. And then they send their votes back to transaction process. Now we enter the second phase of commit. Here, transaction process broadcasts the outcome of the vote back to the participant nodes. And they note this decision in the transaction log. Given that the outcome was a yes, we move on to the post-commit phase. During post-commit phase, we can finally move the contents of the shadow store to the main tables where other transactions can observe them. And also this is where Mnesia sends events to subscribers. Then finally, Mnesia can release the logs held by the transaction, and we're done. So by closely inspecting this protocol, we can already see some inherent performance problems. I already hinted at the first one. During commit phase, Mnesia does selective receives to collect votes and outcomes. So Erlang has to scan the mailbox of the process. Unfortunately, Mnesia does not use a ref trick there. So if message queue is very long, we're out of luck. Thankfully, the solution here is trivial. Just call Mnesia transaction from a temporary process, and that works good enough. But the second problem is much trickier, and solving it is basically the subject of this talk. Imagine that once you add another replica of a table to the cluster, now it has to participate in the vol commit protocol, which is largely a synchronous procedure. And we obviously need to have local replicas of routing tables on all our nodes. So as we scale up the cluster, there is more and more work to sync everything. From our experience, this does not scale well beyond 8 nodes, and then write throughput plummets. This led us to Mria project. We wanted EMQX cluster to be horizontally scalable, and Mnesia was an obstacle on this path, so it had to be fixed. On the other hand, our company was not going to collect any revenue from developing a better Mnesia, because it's a very niche product. So we approached Mria development with the mindset of trying to make use of existing Mnesia code as much as possible. We also wanted to avoid diverging from the OTP upstream too much to be able to update Erlang version easily. We needed extremely low latency dirty reads, but latency of the writes could be sacrificed in favor of write throughput. Because we were already using dirty reads in the hot paths, it was okay to lose some serializability guarantees, but it would be nice to have them as a backup if business logic requires them. That led us to a mixed architecture that combines the existing Mnesia commit protocol with our custom eventually consistent protocol. The idea for solution was very simple. Split large Mnesia cluster into several smaller ones and then somehow sync the data between them. We then simplified the concept even further by assigning each node one of two roles, core or replicant. Core nodes form together a fairly ordinary Mnesia cluster using the protocol that I have just described, but their number can be kept low to avoid the scalability problem. Usually we have maybe 3 core nodes to have just enough in-sync replicas for disaster recovery. The majority of the nodes would be assigned replicant role, and replicant nodes are read-only. This helps to simplify our protocol even further by making sure the transaction logs only flow in one direction. So if a replicant needs to update a table, then behind the scenes, Mnesia sends the transaction fun or a dirty operation to one of the core nodes, which then runs it on our behalf, and the replicant gets the updates to the tables regular way. From Mnesia perspective, replicant nodes simply don't exist, so they can be added and removed freely. So as a bonus, we get an ability to auto-scale cluster. While it may sound like a giant hack, please keep in mind that distributed databases are notoriously hard to get right. And if they corrupt the data or run into a deadlock, it will ruin everyone's day. So one should think 3 times before rolling out your own implementation. We alleviated most risks by intentionally simplifying the protocol as much as possible, reusing battle-tested code, and focusing our testing effort only on the new parts. This allowed us to implement Mria and incorporate it into EMQX in just a few months by 2 developers who did not even work on this full time. So database development is very hard. And as I mentioned, bugs in database engine can cost a fortune. So building an extensive test suite was a top priority. For unit testing, we try to use Concurror as much as possible. If you don't know, Concurror is a tool that goes through all possible scheduling of Erlang processes, so it can find all race conditions and deadlock, provided your system is finite. It helped us to find very rare and tricky concurrency bugs, but unfortunately we couldn't cover the entire code by Concurror tests, because usually it cannot emulate input-output, and Mnesia obviously does a lot of it. So most of the testing had to be done with trace-based Snapcafe test suites. I covered Snapcafe on Codebeam last year. Basically, it's a tool that allows to analyze histories of program execution, inject random faults, and delays into a system to emulate failures, and stress test supervisor trees. Finally, as an experiment, we did a little formal verification with Coq proof assistant to reason about some properties of transaction logs on very high level. Another trick was related to project management. A usable database engine must be both consistent and performant. Generally, consistency is very hard and expensive to verify. We had to employ obvious methods that I just mentioned, and they take a lot of time to set up and get right. While performance is relatively easy to measure, we just throw lots of traffic into a system and see how fast it goes down. So in our development loop, we try to measure performance first, quickly shoot out ideas that did not work, and only then move on to the expensive consistency verification. That helped us to avoid a lot of waste. Fortunately, I don't have much time to dive deep into the design, but I will try to highlight the most interesting parts. First, we added a small patch to our OTP fork to intercept transactions in the post-commit phase. This way, Mria can hook into Mnesia replication flow and intercept committed transactions in real time. When replicant nodes start or restart after failure, they connect to a core node that has the least load, negotiate protocol version, subscribe to a transaction log. And when intercepted transactions are forwarded to replicant node through a bunch of hoops to help with data compression, batch, and whatnot. Nothing special. The interesting part is how we backfill the old data. We call this process bootstrapping, and we came up with a pretty smart algorithm that does not involve any locking whatsoever, so it does not disturb any real-time transactions. Replicant nodes spawn a bootstrapper server process on the core node, and it goes through all the records, reading them using dirty operations, and forwarding them back to the bootstrapper client running on the replicant, which then backfills this data into the local tables. Of course, at the same time, other transactions can modify the table, so obviously this produces a totally corrupted, unusable replica of the table at first. Bootstrapper server and the queue of real-time transactions modifying the data are independent. On this diagram, I will try to represent their progress by the thread pointers. So suppose our first transaction modifies the first record. When the Bootstrap server makes an advance, it reads the updated value. So far, things are good. Now we have the next transaction modifying the second record. Once again, Bootstrapper reaches this record later, so it can observe the side effects of this transaction. But now suppose a new transaction modifies the first key again. By that time, Bootstrapper server already moved on, and it's not going back. So this side effect won't be visible on the replicant node. We just lost an operation. Now Bootstrapper makes another advance and treats the third key. And then yet another transaction modifies it. Once again, we lost a side effect. So if we traverse the tables and update them in parallel, we end up with a replica that misses random updates. This is no good. Or is it? Turns out we can salvage the data if a replicant subscribes to the real-time transaction log before starting the bootstrap process and keeps buffering the transactions while it's running. After backfilling is complete, with some operations missing, as we saw earlier, the replicant can then replay the buffered transactions, and magically it will make the replica consistent. This algorithm is not immediately obvious, so we verified it extensively using both concurror and some formal proofs as well. This naturally leads us to the design of replicant state machine. It goes through three states. Bootstrap, where we backfill the data with creating this unusable broken replica. Local replay, when we replay buffer transactions and fix the replica, and normal, when the local table become consistent and can be read by the local processes. Once everything is done, we just apply transactions immediately to the replica, and local processes can observe the change data with some delay. Unfortunately, this is a very interesting part, but I don't have much time to talk about it. Neither about this and this. Okay, conclusion. Mria project turned out to be a success for us. My colleague, Thales Macedo-Gretezi, did a great presentation on Mria and EMQX performance testing. He did very large scale, very comprehensive testing, and he did a presentation on CodeBeam America last year. So for the performance results, I will just refer to his great talk. It really goes into the nitty-gritty and presents the results that ultimately justified our efforts. But since every talk about algorithms should conclude with some sort of plot, comparing a thing with another thing, I just grabbed a random picture from his talk and put it on this slide, and you see one thing is obviously better than another thing. So yeah, please check out Thales' presentation if you're interested. Conclusions. So Erlang once again proves to be the language of choice for rapid design and prototyping of distributed systems. Concurrer is an extremely useful tool, and I think it's as important as proper. Performance benchmarking should be incorporated into the loop of your development as early as possible. And finally, there is no silver bullet. It is always good to combine different techniques and use their strongest part. All right, that's it. Thanks for your attention.
Thank you very much. Thank you very much, Dmitrii. Are there questions? We have time for one or two.
Can you say something on which kind of property you have shown with coq?
Sorry?
Can you say something about the kind of properties that you have shown with coq? You mentioned.
Okay, yeah. Actually, I can go to the slide. I prepared this, but unfortunately, it's a bit.
Well, by popular demand, you know.
Where is it? So yeah, basically, when we heal the replica with by replaying the transaction log, we end up with a situation where we have a transaction log with some operations dropped from it, and when we can represent this whole bootstrap algorithm as concatenating the complete transaction log with this transaction log with missing operations. So we basically proved that for every possible transaction log, infinite, finite, we can create a random copy of this log with some elements missing, concatenate it with the transaction log, and then apply it to the storage, and then we get equivalent storage to the one to which we applied the normal transaction log. Probably not the best at explaining this, but yeah, basically the last line here is the property. Yeah.
Yep. So what parts did you need to change Mnesia internally, and will this be upstreamed?
We did very small patch to Mnesia TM to simply add a hook point. So it could be upstreamed quite easily. The reason we did not do this is just laziness, because we already maintain our fork of OTP. So it's sort of not a critical task for us. But yeah.
OK, in the interest of keeping time, let's thank Dmitrii, and you can pick him up in the coffee break.